Yeah, so this presentation really builds on what you've already heard today by Elsa. Elsa showed a lot of multiphysics results already, maybe not so much focusing on how you then really obtain this. Sandra said a lot about Neutronics, what are these models that we are actually using in multiphysics. And Pablo, just for the break, explained in great detail how you model turbulent flows, which is also one of the important ingredients of this. And my personal assistant, Jan Lane, is now doing something.
I was full screen.
Yeah, it's a view or something.
Oh, Control Enter Ctrl. Oh.
Thanks. So I'm delivering this presentation, but there's lots of other people that have been involved over the years, because we've been doing molten salt since I think around 2008 or so. Yeah, this one. Okay, so multiphysics is not really in particular anything nuclear, although that's why we are here. I've put some examples on slides where you find multiphysics. Top left, maybe you've been there once in your life. This is one of the Delta works in the Netherlands. Keeps us from having wet feet. And of course, the type of physics involved there is both fluid mechanics and structural analysis. Does this really hold when there's large waves? Top right is a furnace, a glass furnace. So you have coupling between chemistry, fluid mechanics, things like that. Lower left, electronics. And lower right, molten salt, why we're here. So the MSR, now it's of course a very complex system, lots of things going on. And really, we are perhaps able to model all of the subparts separate, but in great detail, we are not able to model the system as a whole. So what we tend to do is, depending on, well, how far we zoom in, we choose a different level of sophistication. So as far as what I will be talking about today is really this part over here. So we're talking about the fuel circuit, which I was not allowed to call primary circuit anymore, and the draining tank. Now this part, the core itself and its fuel, we can do in real great detail, as we have already done in the previous project in EVOL. If you then start to integrate this with the emergency draining tank, then we already have to zoom out a bit as far as the level of detail that we can handle. And if you then would yet expand the model with all the heat exchangers and secondary and third circuits, then we really have to zoom out yet another level by using more system-like codes. So in this talk, I will be mainly talking about this part over here. Why am I doing that? Okay, some short outline what I'll be doing today. Like I said, there's already been a lot of presentations with lots of details about these subtopics, so there's not much overlap there. So I'll really summarize what they said and how we use that in multiphysics models. I'll talk a bit about timescales because that's important, how you couple systems and how complex it really is. So is this really not all that difficult to do, or really is it? Then some more details about actual coupling strategies. So how do you actually couple these codes? How do you exchange data and when? And well, how does that work? And I'll also show in the second half some applications that we've done in previous projects. I'll end up with some conclusions. So now focusing a bit more on the molten salt reactor. What kind of physics do we expect? What's in there? Now we've got a whole bunch of things. It's not even a complete picture. We've got fluid flow, which is highly turbulent. We already heard a lot about precursor movement, which is a special feature of liquid-fueled reactors. We have to deal with heat that's being transferred. We need nuclear cross-sections. We might have bubbles in the system to remove fission products, which may have an effect on the flow itself. And of course, neutronics. And I'm not even mentioning melting, solidification, and other things. So it really is a very complex system with a lot of things going on that you need to model if you want to do things right. Okay, so what kind of transients, if we're really talking about transients, because that's most of the time what we're interested in, not so much the steady state, what kind of transients are we interested in? Well, first of all, we've got transients that have everything to do with the fuel circuits in the core. And the second part is transients that involve the emergency draining tank. So there we're really talking about a multi-stage process. First of all, in a passive system, you need to melt the plug. So that's a question in itself. Second, how long does it take to drain the core to the draining tank? And third, can you keep that salt below a certain critical temperature so that it doesn't start to boil by decay heat? So it's really a three-stage process involving the emergency tank. Now this is a list I took from one of our Samovar results. These are the main transients that we would consider in the multi-salt fast reactor. So a couple of fuel circuits related transients and several that are related to the emergency draining tank. Well, I'll just skip the further explanation here. Now Sandra already gave a very extensive summary of neutronics, and one of the special features of liquid fueled reactors is of course the movement of the precursors, which I've highlighted here in the red box. And for the rest, I would say it's pretty much standard neutronics. If this isn't not your field, then I cannot explain this in any time that I would have now. So I will not attempt to do so anyway. For those who do understand, any other words would be superfluous, I would say. This is just radiation transport augmented with neutron precursors. Now this neutron transport is the way we do things nowadays at Delft. Previously we used the diffusion model. And that's very valid for these large systems. Now to give you some idea of the complexity of all this, how many unknowns are we really talking about? Are we talking about a few thousand or what? Now I did a little bit of math here. So if we talk about a mesh of about 10,000 spatial elements, which sounds reasonable to me, maybe 24 angles, 8 precursor equations. If you're talking about finite elements and we use linear polynomials, you got 4 basis functions per element. And in energy, we might have something like 10 groups. And you end up with 10 million unknowns. And it's not just a steady state problem, but this is a time stepping issue. So every time step, I need to do 10 million unknowns. So it's a pretty decent sized problem. So in green, diffusion is really quite a bit cheaper. Now something about timescales, I think that's really important if you talk about the physics of these systems and how to couple them and when to exchange data. There are really 2 important timescales in neutronics. These are taken from point kinetics theory, but is almost equally valid if you do it more complicated. There's essentially 2 timescales in the problem. One has everything to do with the lifetime of neutrons in the system. So we're talking about less than milliseconds. And the other has something to do with precursor decay, and which is a very long time scale compared to the neutron lifetime. So we're talking much larger than a second. Now most of the time, we are really not so interested in resolving this prompt jump, except if you actually have a prompt jump. So in most cases, you're not so much interested in processes that are related to this particular physics. So that means that most Neutronics codes are implicit in time to make sure you don't have to use this time step. Yeah, or you can use a trick using the prompt jump approximation directly, and then you don't have that time scale at all. Now, what do people use? Most people use diffusion codes, and they're either homegrown, like we used to do, or they are built into, for instance, OpenFOAM, which is good in handling diffusion type problems. So that would be a cheap choice there. And nowadays in Delft we use full transport. Now, inevitable in Neutronics is that you need, of course, the proper cross-sections. Now I'll just start with the end statement here on the slide, that cross-section generation has always been somewhat of an art. Maybe nowadays it's no longer completely true because cross-section processing can be done by Monte Carlo methods. So the real tweaking art has disappeared a bit from it. But if you use, let's say, deterministic cross-section processing programs, it still is a bit of an art. Now, in general, of course, cross-sections depend on space and time through temperature and composition. If you have many millions of cells or tens of thousands of cells in your problem, you will not use tens of thousands of different sets of cross-sections, just over the top. So what you will do in practice is you designate for each of your computational cells a specific type of material. If I would move ahead a bit on this slide, in practice what you would do is you would cut up your reactor system into a number of regions, here designated in the red boxes. And here there are, how many is that? 6 times 6 or something? Something like 40 regions in this case. And each of these regions then has an associated material. So this could be salt number 1, this could be salt number 2, blanket 1, blanket 2, and so on. Now, of course, there's not just one salt or one blanket because there are different positions in the reactor. So there's a different spectrum, and therefore there are different collapsed cross-sections. Just going back, in general, I would say people use between something like 20 and maybe 1,000 regions. That would be more than sufficient to handle all the spatial dependence. So you have to deal with somewhere between 20 and 1,000 cross-section sets. These cross-section sets are usually pre-built. So you do your cross-section processing before you start, and you build cross-sections for a specific set of temperatures. So going back to the next slide again. For any, let's say, computational cell somewhere here in this green box, so green is the actual spatial mesh, it is within this red box, so it belongs to a certain material type. And for that material type, I would then, for a given temperature, calculate what the cross-sections are by interpolating between the libraries that I have. Now, you generally tend to interpolate on a log scale due to the Doppler effect. And there's still also, there might be an effect of the density if you might have bubbling in your system. So it's just not completely salt, but it's for a percentage not salt. No, I think that's about it. Then flow modeling. Building upon what Pablo explained to you, most of the time we use Reynolds averaged Navier-Stokes modeling, which is essentially the cheapest option there is. This is a really big reactor with a very, very high Reynolds number. So you can just forget about doing a DNS or possibly also an alias for the whole system. So a RAND calculation would be the most sensible thing to do. Well, these are the RAND equations that Pablo already mentioned. And, well, any turbulence model could of course be augmented with this. So it's maybe K epsilon or K omega or whatever. To give you a similar estimate of how difficult this problem then is compared to the neutronics, usually the mesh of the CFD is a bit finer than of the neutronics. So I've written here something like 40,000 elements in 3D for a pie-shaped segment of the MSFR. Again, using a linear basis, there are 5 main flow variables, and you have the turbulence model to take into account. That comes down to about 1 million unknowns. So it's considerably less than the neutronics, but neutronics was linear, and this is nonlinear. So in general, you tend to spend more time in your CFD than on your radiation. It's just a more difficult problem. Again, here also something about the timescales that are relevant in the problem. Now, it's very turbulent flow, so there's a whole range of spatial and timescales in the system. Let me just only deal with timescales here. The largest timescale in the problem is the large eddy turnover. So essentially, it's the time to move from your inlet towards your outlet, something like that. It could be of the order of about 10 seconds in an MSFR. Another timescale that's relevant is the cascading or decay time. It's probably much less than a second. So how long does it take for turbulence to decay? And very much on the small scale side, we have the Kolmogorov timescale. How long does it take for energy to dissipate when it's at the small scale? Now again, we use RAND calculations, so we really do not resolve anything that has to do with these small scales. They're simply not there anymore in the model. But we do model in RAND models this cascading, and this timescale can be pretty small, so that is also then handled implicitly to make sure that we can use time steps that we actually want to use in the system. And maybe on a more general note about timescales, so I've explained a bit about timescales in the neutronics, and these are some timescales of the CFD. Now this plays a role if you couple the two physics parts together. Imagine that your physics block number 1, I don't know whether it's CFD or your neutronics, is very slow compared to the other physics. That means that if you take data from that physics block, they don't change a lot over time. So if your other physics takes data from there, you don't really need to update it all that often. So it really has a consequence for how often you exchange data from one block to another, and vice versa. Now we're exchanging data between code systems. And how does that, well, what's important there to take into account? Each of the physics problems has their own mesh. CFD is more complex, more particular about its mesh also. Those meshes tend to be more refined than neutronics. So you have two physics problems on different meshes, and you need to exchange data. And what's important in sharing this data? The first thing is that you have conservation. If you do multiphysics with CFD and neutronics, you're taking essentially your power density from your radiation transport code and you put it in your CFD. And you want that to be conservative, otherwise you just simply lose fission power. So conservation is one thing. The second, of course, is the speed. Now, if you use things like codes like OpenFOAM, all these transfer functions from one mesh to another are available, and maybe you don't need to know what's inside. But if you start doing these things yourself, you do need to know. And how we do things in Delft is that we have a sort of a master, whatever mesh that is, in black, in thick black. And both the CFD mesh as well as the Neutronics mesh are based on that master mesh. And it can be locally refined. And as long as they share this master mesh, everything is fine. Because it's very easy to project a solution on this mesh to this particular mesh. So we use hierarchic meshes, starting from some kind of master mesh that they both share. And then data can be exchanged very easily. And of course, well, here it's drawn as squares, but this can be done on any type of finite element. So tetrahedra or whatever. Now I think one important thing about coupling is, well, how do you do this coupling? Conventionally, if there are two types of physics in the problem, so let's say CFD and Neutronics, conventionally it's also called loose coupling. You would run your physics code number 1. You would take the output from that, put it in your physics code number 2, and essentially that's it for that particular time step. And you move on to the next time step. Physics code 1 uses some data from physics code number 2, and this process goes on and on. So it's really cheap because you run each code only once per time step. And it's really easy to do. I mean, you just call each of the codes, you maybe through files you exchange the data. So up to maybe 10 years ago, most of the work was done like this. And quite honestly, there's really not all that much wrong with it. Most of the time it does work. One of the problems, if you're really looking for very high order accuracy, you cannot do it like this, because at most this will be first order time accurate. Now, the other thing is stability. Even if both of these codes are implicit, you're still restricted in time step, just because you're just not iterating. So our more different scheme is tight coupling. It's really not all that different. What you do is you iterate in a time step. So you go back and forth until you're done. Everything is converged. You step onto the next time step and you start iterating again. And that's the only difference. So you really converge out all the nonlinearities and then you move on. And then this is called tight coupling. Now it's still easy to implement, but the efficiency really depends on how long this takes. That is nonlinear iteration. How many times do you need to do that? Now, in practice, if time steps are small, usually that goes pretty quick. So let's say you do 3 iterations or so. But if time steps are larger and larger, then you get yourself into trouble. So to increase efficiency then, it's all about this within a time step to make this efficiently happen. And well, people tell, if you just do these one after another, formally it's called a Pocari Iteration, and it converges only linearly, so it could be slow. And there are some variations of this, Anderson and Aitken, and they tend to be a bit better, but still perhaps not so satisfactory. But then if you go to back to your bachelor or your master's phase, you learned about, usually the example taken is to calculate square roots of something, like the square root of 8. How do you do that? Well, you formulate it as a nonlinear equation, x squared equals 8. And you can solve that by Newton iteration. And it's a really efficient process. Every step you gain multiple digits. So why not just use Newton iteration? That's quadratic convergence. The problem is it requires the Jacobian. And in practice, with these big codes, you don't have the Jacobian. Most of these codes are even black boxes, so there's no way to get these things. So is there then still a way to do Newton iteration with quadratic convergence without a Jacobian? And it turns out there is. And it's called Jacobian-free Newton-Krylov methods. Now in about 2008 I was also, then this became somewhat hot in literature. Everybody was raving about JF&K, and I really didn't know what it was. So I put a student on that to find out what it was. He did his bachelor work on that. That's how it works in academia. If you don't know, you ask a student. And it turns out not to be all that complicated. It really is a combination of three things. First of all is Newton. Second is that you use, for your linear system solve, you use a Krylov method, which is a modern linear algebra method of solving linear systems. And you use a smart trick. So the combination of these three things makes up for Jacobian-free Newton-Krylov. Now, how does it really work without this Jacobian? It turns out you have to solve a linear system in each Newton iteration. If you use a Krylov method for that, you normally need the matrix vector multiply. So you have the Jacobian, which is some kind of a matrix, and you multiply that with some kind of vector. That's all that's required. But how do you do that if you don't have the Jacobian? Well, it turns out that you can formulate this matrix vector multiplication in terms of the residual of what you're trying to solve. So if you can calculate the residual of your system, so the error, then you no longer need the Jacobian. So that's essentially the trick behind JF&K. And an epsilon is a small, turns out to be difficult to choose, but it's a small number. So now you can do Newton without a Jacobian. Now the student, of course, worked really hard, and did a couple of examples. And it does show you what the problem is with this traditional loose coupling. This is a, you could say, single physics problem, that of a conducting rod. And there's a temperature given here and a temperature given there, and they're oscillating. So that's what you see here. And this is the exact solution to the problem. So these boundary temperatures are oscillating and heat is conducting all over the place. And what do I then do to make this a multiphysics problem? I simply cut this thing in the middle. Then I've got two physics problems that are, well, they're connected together through the boundary condition. So it's sort of an artificial multiphysics problem. And if you then do loose coupling on this problem, so the traditional method, then you see that you get yourself a bit into trouble here where the physics get coupled. This doesn't really seem physical. This is the true solution, nicely smooth here, and loosely coupled for a rather big time step. It's a bit strange. So you get these artifacts with loose coupling. And this is then the Jacobian free solution, which looks just fine. And so for large time steps, it really makes sense to have tight coupling and iterate out of the problem. Or you may have some of these artifacts. And another example, which is a bit more close to home, is an MSR loop. And this may answer one of the questions that was asked somewhere in the morning, I think, if you could use point kinetics in a molten salt. I'm not now stating what the quality of that would be, but you can simply do it. We've got a problem here that you have the reactor core. We use point kinetics, so we calculate the power, but we do distribute it over the core in a cosine way. So the cosine is fixed, so that's not very physical, but it still is point kinetics. And for the rest, all of the other processes are included. So precursors are actually pumped through the system in the wrong way, I guess. I couldn't find the reverse picture. And it contains all the physics that you would normally have in an MSR. Now we try to put the JF&K method through its paces, just see what it can do, can it handle things you want, by putting a external reactivity into the system. and then monitoring neutron density, precursors. And I can't really read it from here, to be honest. The temperature. And it turns out that JFNK is really stable and works very well for large time steps, except if the external reactivity is extremely high. So if it's very much larger than beta, then the time step choice does make a difference. Sometimes you get non-physical solutions. Okay, so I'll use the remainder of the time to give a couple of examples of what we have done in Delft about coupling. And the first example is the MSRE. So this was work we did around 2008 and 2009. And so the MSRE, we've already seen this picture somewhere in the morning, or maybe yesterday. It's essentially a big pile of graphite with channels drilled into it. And we built a three-dimensional code system for this, so back in the days. This was diffusion-based with an in-house code system. And it's not really a CFD problem, of course, because you have all these channels. That was also highlighted by Pablo earlier. You really have simple channels which you can just specify. It's not real CFD, you could say. So this is a bit of a side view and a top view of the Neutronics mesh. Not all that fine, but it's adequate. This was done in an XYZ case. So it's sort of a staircase approximation. Our current codes are, let's say, more capable than this. Cross sections were processed by the scale code system, 8 groups, and albedo boundary conditions were used for the control rods. A more detailed view of these, let's say, the lattice cell. In red, you see all the graphite and this computational mesh that's used for the conduction. And in green, you have the molten salt channels, where we use this one-dimensional flow code, let's say. Each of these channels have been modeled separately. So there are over 1,000 channels. So we use over 1,000 sub-channels separately. And the graphite block has been discretized completely. So that's over 1.5 million cells that essentially couple all of these channels together. And so here the multiphysics is really lots of sub-channels and one big pile of graphite where you have heat conduction. Now I'll skip this. In practice, it sounds so simple to say, well, you just couple of codes you put together, you exchange some data here and there, and you run it one after another. But in practice, these computational schemes tend to, well, get complicated quite easily. Now I think this is one of the pictures that's done a lot for the MSRE. It's the pump startup. You essentially have a 0 power reactor, only 1 watt. You start at a certain power, you start the pump, you pump out the precursors out of the core, and you lose reactivity, so you lose power. And at some point they get back into the core and power goes up again. And then this is of course the time scale of recirculation that you tend to see. And this goes to 0. And from a side view you see these precursors indeed being convected out of the core, and then at some point they return. And so that's the oscillation that you see. Probably not go through everything, let's see. Yeah, this is a side view. You can also see here this channel structure. So this is simply a cut through the graphite. You see this is the graphite itself, and then you see all the temperature of the specific fuel channels. Now if you make a bit of a zoom into one of the fuel channels and the surrounding graphite, you see that here you have a dip in the temperature. That's the salt channel, and here's the graphite surrounding that. So the graphite is at a higher temperature than the salt, because you deposit heat into the graphite, which then has to be removed to the salt and then convected out. And there's only a few degrees difference. Now let me skip this. This is more interesting. And the real strength of multiphysics codes is accident analysis. So up to now we've seen maybe some toy problems, some toy transients, you could say. But these codes really make you give you tools that you can use for hypothetical scenarios. Now this is very relevant for the MSR. So let's say what happens if you have some kind of a blockage of your fuel. So maybe one or two of your channels get blocked. And then what happens to the system? And these kind of codes, coupling Neutronics and CFD, although maybe not full CFD here, you can really address these issues. So here we assumed that some of these channels were partially blocked. And partially blocked here means that the mass flow through these channels, which was prescribed, was reduced by 80%. Now you then start your multiphysics simulation and you see what happens, and then you see that these hotspots in the reactor core start to arise. And the heat that's deposited in the graphite is no longer effectively removed by those channels because the velocity is lowered by just 80%. So the heat is no longer effectively transferred to the channels, but has to diffuse out through the graphite to other channels. So it's one physics that now take care of what used to be local, but is now sort of transferred to other channels. So it's called the debris accident. Now and then same in the sides, in a side view. Another example I just wanted to show is that of the previous molten salt reactor project, EVIL, which was led by CNRS and was already addressed by ELSA. Now it was a bit, the starting point of EVIL was of course different than that of Semaphore. In Semaphore we use a different geometry than is given here on the slide. But results from EVIL have of course made us choose this different design in Semaphore. This was also already shown by ELSA. Now here's a picture that was used for essentially a benchmark on multiphysics. So all the participants were doing calculations on CFD and Neutronics for this particular system. And we also did that, and we did this in a 2D RZ geometry. So let's say this is of a lower sophistication level than we would do in Semaphore. And we're progressing, let's say. That's the idea. I will skip this. So this is one of these pictures that sort of tends to hide how complex it really is. So you've got some CFD code, you've got a Neutronics code. They interchange the power density and the velocity, or maybe the turbulence viscosity. You mix your cross-section set for given temperatures, and then everything runs. That's just a simple picture. In practice, it really is a bit more complicated. Now, I think some of these pictures were already shown, also by Jan Leen. The steady state velocity field for the EVIL MSFR looks like this. So remember, this was the straight, still the straight blanket boundary. And you got a large recirculation and some small recirculations in the corner. And if you then look at the temperature profiles that correspond to this case, then you see that, well, you get a really hot region and rather heterogeneous. So this made people in EVIL choose for a different geometry. So where this blanket boundary was no longer straight but curved. So you get a much smoother temperature profile. Yeah, and that is then the starting point for Samovar. Oh, maybe some interesting physics here. The precursor concentrations. This is the longest living group, and this is the shortest. Of course, for the longest living group, they tend to go around a couple of times before decay, so they get mixed all over the place. So it's very uniform. On the other hand, the very short-living precursors tend to decay already before they, well, when they enter the downcomer, the heat exchanger region and the pump. And so this tends to follow rather the power density, except with a slight shift. If it were really zero decay time, it would just follow the power density. And this is the intermediate, which is sort of in between. Now again, here too, the real strength of multiphysics is into accident scenarios. And one of those scenarios is a loss of flow. And here, I guess, well, I can't really remember exactly, but it was ramped down in a very short time to either 0 or a very small value. And you see that in a very rapid initial transient, your flow tends to decrease by a very large amount. And if you wait long enough, then you get into a natural circulation mode, where the total flow is about 1/5 or 1/6 of the initial one. But still, this is a rather benign transient. The last transients that I just want to discuss only very briefly before I end is that of reactivity insertion. I think a lot of remarks were already made about that by Elsa. So what happens if you were to add too much fuel to the reactor? So you'd have a reactivity insertion. A somewhat prompt jump-like power increase occurs, but limited by thermal feedbacks, by Doppler. There are of course also some delayed effects by the precursors, and then you get into a very complex interplay between flow, temperature, and feedback, which you really cannot predict by anything else than these multiphysics codes. Certain transients perhaps you could do a bit by hand in a sense, well, this would happen and then that, but if you're really interested in the details, you're stuck to using these codes. And you can then have some pictures of results for different values of the reactivity insertion. It's hard for me to read from the side, it was 250, 265 PCM and on below 533. And this was instantaneously added. So you start, your power increases, you get feedback, and then you get into a rather complex part, which is hard to simply explain by thinking about it. And you end up with a new steady state that's just barely higher than your initial state. And so these two are rather benign transients, you could say. Okay, so some conclusions on multiphysics modeling. There are nowadays high fidelity code systems available. So we have built a system many years ago which was used for evol, and now we're essentially working on a new system for Samovar, which is, let's say, higher fidelity than it used to be. But other groups also have systems available: Milan, PSI, CNRS, and others. The realism of these simulations is continuously increasing. So in evol, we really looked at the core and what happened to this fuel circuit. Within this project, we're also going to extensively look at the emergency draining tank and into bubbling. So the physics is really improving. And I think the most important message is that these tools are really indispensable for safety analysis, especially of a complex system such as the MSR. For certain types of reactors, you might really think about what would happen in certain transients, but for the MSR, it's really, I would say, one step more complicated, just because of the flow phenomena. Maybe it sounds like, well, you just couple these codes together and then you will get your results, but the problems are still rather immense, especially in the sizing. And so more than, let's say, 10 million unknowns for each time step is really a big problem. And perhaps in the future we'll include even more physics into this, like the coupling with the chemistry and, well, who knows what. Well, here you can read a couple of publications that we did in the multi-salt area. A couple of downloads also, although this address is probably not long lasting, I would say. It's probably subject to quick change. So, thanks very much.